Alright, so continuing on from last lesson, we first looked at the whole idea of a series, which was adding all the terms in a particular sequence. We're going to now look at geometric series. So just like arithmetic series, where that was the sum of the terms in an arithmetic sequence, geometric series will just be the sum of the terms in a geometric sequence. So the notation that we use s with a little subscript of n, and that denotes the sum of the first n terms. So for example, something like s6 would mean that you would take the first 6 terms, so t1 plus t2 all the way up to t6. Okay, so we have our general term here to generate whatever term we want from a geometric sequence, and a series is just going to add the first n terms of that sequence. So for example, let's say we have the sequence 1, 3, 9, 27, 81. Well, S5 would be adding up the first 5 terms, so that would be equal to 1 plus 3 plus 9 plus 27 plus 81. Okay, so you can quickly run that through your calculator and see we'd wind up with 121. So, I mean, obviously we can add up all the terms by hand, but if this were a much, much longer sequence, let's say the sequence continued, we wanted to find the sum of the first 80 terms, or the first 100 terms, it would take obviously a very, very long time. So hopefully there's some kind of formula that we can use to try and shorten that up, just like we did with arithmetic series. Okay, so what we're going to do is to try and generate a formula. We're just going to take, if we have Sn, remember that's just adding all the first n terms of a sequence together. Okay, what I'm going to do is I'm going to rewrite each of these terms using the general term of a geometric sequence. So if we have a geometric sequence, the first term is just going to be a. Then the next term is going to be a times r, because we always multiply by a common ratio to go from one term to the next. So then we add, it's going to be ar squared, and as we keep multiplying by r, our exponents in r go up, and eventually we get to the point where we have plus ar to the n minus 2 plus ar to the n minus 1. Okay, that's going to be, again, using our general term for a geometric sequence, the nth term. Okay, and then what I'm going to do is I'm going to take this entire row right here, and I'm going to multiply every single term by r. Okay, so just to show you what's happening between here and here, I'm multiplying r by everything that's on that previous line. So that's going to give me ar plus ar squared plus ar cubed. So again, the exponent of each of these terms, the exponent on the r in each of these terms is going up by 1. This keeps going all the way up to here. I'm going to have ar to the n minus 1 plus ar to the n. Sorry, a times r to the n. Okay, and finally from there, it seems like I'm just sort of doing things randomly, but I'm going to lead somewhere with this. I'm going to take the second line here and subtract the first line. Okay, second line minus first line. So anything that's a like term is going to be subtracted, so it's going to be canceled away. So here, for example, when I subtract, I'm going to have ar minus ar, so those are going to cancel. I'm going to have ar squared minus ar squared. Again, those are going to cancel. In fact, if you keep going, the ar cubes cancel, the ar fourths will cancel. The only things that won't cancel in the end are going to be two terms, this ar to the n and this a. So if we actually do a full subtraction here of the second line minus the first line, all we're left with is a times r to the n minus a. So you may wonder, okay, well, what's the point of this? Well, I'm trying to develop a formula for Sn, so I'm going to try and use this equation and solve for Sn. What I'm going to do on this side is I'm going to factor the Sn out of both terms over here. So if I do that, I'm going to have Sn. What's left over from this term is going to be r. From here, it's going to be a 1, so we have r minus 1. And what I'm going to do on this side is notice I have an a in common from both of these terms. I'm going to factor out an a. So I'm going to have a times r to the n minus 1. Okay, and then all I really need to do now to solve for Sn is divide both sides of this equation by r minus 1. So divide there, and all of a sudden Sn is now isolated, and I get a formula for a geometric series, which is a times bracket r to the n minus 1 all over r minus 1. Okay, if you want, you can have a different form of the equation where the a is multiplied through this bracket, but that's not necessary. This equation here is a little bit easier to work with. So again, now we have a formula for the sum of a geometric series. Okay, so now let's use this formula to hopefully shorten up some of the problems we can do. But before we can do that, let's just summarize everything we know now about arithmetic and geometric sequences in series. So mainly in terms of trying to find the general term, we know from arithmetic sequences that Tn is going to be a plus d times n minus 1. Okay, and then for geometric, the general term is generated by a times r to the n minus 1. Okay, if we're looking at summing the first n terms of that sequence, we're looking at arithmetic series and geometric series. So for the arithmetic, we saw two different formulas. We saw n times 2a plus d times n minus 1 all over 2. And we also saw one version which involves the first and nth terms of the sequence, so t1 plus tn all over 2. Okay, and finally for geometric series, we now have this last little formula right here. Okay, so this is a summary of sort of like your toolbox to solve different types of problems involving arithmetic and geometric sequences in series. But for now, let's practice the geometric series. So for each of these cases, I want you to find S7. So again, that means the sum of the first 7 terms. With some of these, again, if you recognize they're geometric, you can follow the pattern, find the first 7 terms, and add them together. But let's try and use the formula to try and shorten things up. So looking at this first one right here, we're going 2, -8, -18. Now, what kind of sequence do we have here? Is it arithmetic, geometric, or neither? So as we go from 2 to -8, if it were geometric, this would be multiplying by -3. But that pattern does not hold here as we go from -8 to -18. -8 times -3 is not -18, so we can't use that one. It's not geometric. Let's see if it's arithmetic. So to go from 2 to -8, we're going to subtract 10. And does the same pattern hold as we go from -8 to -18? Yes, it does. So this one here is actually arithmetic. Okay, so it's arithmetic. Our first term a is 2. Our common difference is -10. So let's find S7. So using the arithmetic series formula, which we now have on the previous page, I'll just write it out here so we have it as reference. Okay, so in our case, n is going to be 7. A is 2. D is -10. Okay, put in the n equals 7 again. Okay, the big thing to watch out for here is just make sure you're following order of operations. It's very easy to make a little algebra mistake here. So here I have 4 minus 10 times 6 all over 2. So we're showing up with the -196 for being the sum of the first 7 terms. Okay, so what I'd like you to try and do now, there's 3 other sequences on this page. First of all, I need you to find out if they're arithmetic, geometric, or neither. And if whatever the case is, I want you to then find the sum of the first 7 terms. So try them all on your own or with a partner, and push play and try to go through them together. Alright, so we can take a second here and check your answers here. Looking at B, this one's a geometric sequence. It's a common ratio of -4 to go from one term to the next. So you have an A value of 5, our first term. R is -4, and since we're trying to find S7, N is 7. We take our geometric series formula, we throw in everything we know. So again, A being 5, R being -4. And again, just watch your algebra. When you use -4 to the exponent 7, you should get -16,384. Minus 1 gives you -16,385. And when you simplify your denominator there, should be -5. When you simplify it all, you get 16,385 as your overall series. So looking down at C, the terms don't change, right? They stay as 7 every single time. So if you want to try and think of this as arithmetic or geometric, you can. I mean, if this were to be arithmetic, you would have an a value of 7 and a common difference of 0. And if you really want to, you could use the arithmetic series formula. If you want to treat it as geometric, you could, again with an a value of 7, but your common ratio here would be 1, so again, not particularly exciting there. But the easiest thing there is if you recognize that all the terms are 7 and there's 7 terms in your sequence, well, the sum will just be 7 times 7, which is 49. So do things the easy way whenever you can. Looking at D, D is neither arithmetic nor geometric. There's no common difference or common ratio to go from one term to the next. If you look at the pattern, though, this is really just, first term is 1, which is really 1 squared. Your second term is 4, which is 2 squared, and then 3 squared, and 4 squared, and so on and so forth. So you can always generate each term by taking the term number and then squaring it. As it turns out, your general term is just Tn equals n squared. So we can find the next 3 terms just by following out the pattern. So we get 25, 36, and 49. And so even though we don't have necessarily a formula for the series of this one, for the sum of the first 7 terms, we can just add up the first 7 terms manually to get 140. Okay, so let's take a look at the next example here. So now I'm asking you to determine the sum of negative 6 minus 12 minus 24 minus and so on and so forth, all the way to minus 6,291,456. So I want you to try and find the sum of all those terms. Okay, so give it a try on your own, see what you need to figure out in order to get this to work, and push play to go through it together. Okay, so there's a lot going on in this one. So first off, what I did is I wrote out each term separately so I could see it as a sequence a little bit better. So when I look at each term, negative 6, negative 12, negative 24, I see there's a common ratio to go from term to term. So this is a geometric sequence. It has a common ratio of 2 and a first term, an a of negative 6. The only thing is here, before I try and find the sum of all these terms here, I need actually to know how many terms there are to begin with here, because in order to use that formula, that geometric series formula, I need to know how many terms I'm adding together. So I don't know n, but what I can try and do is I can use a general term to try and figure out which value of n gives you a term value of this negative 6,291,456. So I start with the general term here, and so Tn equals AR to the exponent n minus 1. I know the value of the term is going to be negative 6,291,456. I put in my a and my r, and once I had this equation right here, I had to try and solve for n. So I divided both sides of the equation by negative 6, and when I did that division, I got 1,048,756 equals 2 to the n minus 1. Now you may remember from exponential functions, and from an example we did earlier this unit, exponential equation where the unknown's in the exponent. The only way we can solve that is by having a common, having both sides of the equation under a single power with the same base, with a common base. So if I do some experimentation in my calculator here, I'll discover that this 1,048,756 is actually 2 to the exponent 20. So once I do that, I now have both sides under a single base of 2. So I can equate the exponents. So 20 is going to be equal to n minus 1, and then I find out that it's going to be the 21st term that's equal to that negative 6 million. So now that I have n, and I have a and r to go with it, I can use my geometric series formula. I throw in my a, I throw in my r, I throw in my n, and then I simplify as much of it as I can, and I bring it down to having a S21, so the sum of the first 21 terms, or the sum of everything that's up here, is going to be negative 12,582,906. Okay, so there's one last example to go through, and it's a word problem. So I lose a bet with Scott, and I agree to pay him a penny or a cent on day 1, 2 cents on day 2, 4 cents on day 3, etc. And I want to know how much I'm going to be paying Scott on day 10, then how much will I have paid him in total after 30 days. So I want you to think about this one, try and set it up, and we'll finish this up in part 2 of the lesson.